Okay, welcome everybody. It's a pleasure to have Barbara Dembin talk about large deviation principle for streams and maximal flow in first passage percolation.
So thank you for the invitation. So let me first introduce you the model. So we are going to work in dimension d greater or equal than 2. And we are going to consider omega, that is a bounded connected domain of Rg. So it will be a really nice and regular domain. So we really regular with regular boundary and so on, but I don't specify all these things. And we are going to consider two subsets, gamma 1 and gamma 2 of its boundary that are going to be two disjoint subsets. So we have, for instance, gamma 1 here and gamma 2. They are not necessarily connected, but they have to be, gamma 1 has to be disjoint of gamma 2. And we will see that gamma 1 will represent a source, so, and gamma 2 a sink. So we will understand this, why we call them that way in just a moment. And we are also going to consider a distribution G on 0M. So for some, and we are going to consider the rescale lattice in RD. So we rescale the lattice by a factor n, and of course we will want to let this n go to infinity later. And we will denote by E and D. It's just the corresponding edges, so the small edges, the regular edges of ZG, but that have been rescaled. And so the first passage percolation model is to consider a family of IID random variable indexed on the edges and of low G. Okay, so this is a standard model of first passage percolation. And if you have already heard of first passage percolation, I guess what you've heard of is that this random variable represents passage time. But here we are interested in another interpretation. That means here this random variable t won't represent passage time, but they will represent the capacity of the edge E. So it's not a capacity in electrical sense. But what we are going to do is that we are going let water flow in the rescale lattice, and we are going to be interested in a stationary circulation of water in the lattice. And TE will represent the maximal amount of water that can pass through the edge E per second. So it's capacity in the sense of there are going to be water that flow in the lattice, and you can see each edge as a tube that is bigger or not, depending on its capacity. Okay. And so that's why we call gamma 1 a source, because that will be the place where the water will enter, and gamma 2 will be the place where the water will exit. And so, of course, we need to discretize omega and the source and the sinks. But here I will just pass these details, and we will do as if there were no discretization problem when we look at the rescale lattice. So as I said, we are interested in the stationary ways of circulation of the water in the lattice. So to be able to describe that, we have to say for each edge, how the water circulates. So there are two important information. For each edge, we want to know the amount of water that circulates through that edge, and also the orientation. So to encode that, we are going to define admissible streams. So a stream is just a function from the edges, and then there are several ways to encode it. Here we are going to each edge give some number in RG. So I will it because it will have an importance in what follows. But let me quickly explain how we give what does FNE mean. So if we look at the norm of FNE, it will represent the amount of water that circulates through the edge E. And actually, FNE is going to be parallel to E, and given the direction of the vector, we will be able to recover the orientation. So I don't want to be too formal, but what you have to remember is that for each edge, you have to give these two important information, that is the amount of water that circulates through that edge and in which orientation. So for what follows, it's more convenient to encode it in RD, but of course there are other ways to do that. Okay, so for instance, for the moment, this is just a stream, and to be an admissible, the word admissible means that we want it to be physical. And so for a stream to be physical, the thing we want it to respect is the node law. So we want that Fn respects the node law everywhere except for the source and the sinks. So again, I don't care about the discretization issue. Okay, and the
node
yes?
law means that what goes in comes out.
Exactly. I'm about to say it. So the node law is that for each node, the amount of water that arrives at the point is equal to the amount of water that leaves the point. So it's just the node law in the physical interpretation, standard physical. So it's just to be, it just means that there is no loss or gain of water inside the omega. But of course, in the source and the sinks, this is where we can lose or gain water, because we want Fn to be equal to 0 outside omega. And of course, the last condition that we want it to respect is to respect the capacity of the edge. That means we won't be able to let more water flow than the capacity allows it. So this is just. So this is for OE. So
don't we need to pay attention to T of E? I mean,
yes. Sorry. Yeah. Thank you. Yeah. Sorry. Thank you. Of course, it was T of E. Otherwise, nothing would have been random. So of course, the only place where the randomness comes from here is TE. So here we have defined admissible streams. So the set of admissible stream is random because of this capacity constraint TE. And we are interested in for a given admissible stream, an interesting quantity will be the amount of water that circulates through omega. So the amount of water that enters by gamma 1. So we do not exclude, you see in the definition, we do not exclude the fact that water can exit through gamma 1. So when we look at edges, we will have things like that. And what we want is to define is, so again, won't be too formal. We want to define the flow of Fn. And this is just the sum over all the edges that are going to be, so this is the edges that are going to enter omega through gamma 1. And we want to, so it's a plus or a minus depending if the water is entering or exiting. And so it's again very physical, so I don't want to be too formal on that. It's just the amount of water for a given stream Fn that can enter through gamma. So if it's not clear, do not hesitate to ask questions. So for a given stream, admissible stream Fn, we can define this quantity. Of course, because the node law is respecting the amount of water that enters through gamma 1 will be the same that the amount of water that exits through gamma 2. And we are interested in the maximal flow, that is the maximal amount of water that can enter through gamma 1. So phi n is just the supremum over of flow Fn over all Fn admissible stream. Okay. And actually we can prove that this is a shift, so this is actually a maximum. And we call, so this is maximal flow. So. And a maximal stream, there can be several. So we call Fn max is such that phi n okay. And so first question would be to ask what is the typical order of this maximal flow phi n. So with the this definition, it seems natural to expect that the order will be n to the power d minus 1. That is the order of the surface. And once we know the order, another natural question would be to ask if do we have a law of large number? So when we rescale phi n by n to the power d minus 1, does it converges? And the answer is yes. So it has been proved by Raphaël Serre and Marie-Thérèse. So under some condition on regularity on omega that I don't specify, we have that there exists phi omega. So it can be 0 if the law G has a too big atom in 0, but we exactly know when it happens. So there exists a constant phi omega that will only depend on the distribution G, the set omega, and also the sources in the C. But that is deterministic, depending. Such that so we have a law of large number for the maximal flow. So in this talk, we are going to be interested in upper large deviation of the maximal flow. So what is upper large deviation? So now that we know that we have a law of large number, we want to understand how the following probability behaves. So if we take lambda that is strictly greater than phi omega, we want to understand how this probability behaves. So the first thing when we want to do upper large deviation, when we want to study that, is to understand what is the order of large deviation. So this probability will decay, and it will decay exponentially fast, and we have to understand what is the correct decay. So I'm going to try to give you an intuition of this decay. So maybe it will be a bit fast. So if you never heard of the max flow min cut problem, maybe you won't understand the 2 next minutes, but it's not important in what follows. So, okay, so let me explain you what so there is a theorem from graph theory that is the max flow min cut theorem, but it's actually a very intuitive theorem. So if you look at a maximal stream, if it's maximal, it means that you cannot let more water enter. And actually, the fact that you cannot let more water enter will imply that somewhere in the domain, you will have a blocking surface. That it's a surface where all the edges are going to be saturated for this Fn max. So in these edges, Fn max of E will be equal to TV. So it will act as a bottleneck. It will prevent more water to enter. And this is a surface that separates the sinks from the source. And what the max flow min cut theorem says, it says that actually Phi is also equal to the minimum of the capacity of a surface for the surface that separates the source from the sink. Surface. So that's what the max flow min cut says. And it's easier with this definition to understand what is the correct deviation order for the upper large deviation order. But maybe the simplest deviation order is the lower large deviation order. So if we want to study the probability that phi n is smaller than this for some lambda and strictly smaller than phi omega, it's actually much simpler to understand the deviation, because what we have to do to create such a lower large deviation event is just to, along a surface, decrease all the capacity. And this will have a cost of surface order. And indeed, we can prove that the lower large deviation decay as with a surface order. Whereas the upper large deviation, you see it's more complicated than that, because it won't be enough just to increase along a surface all the capacity of the edges, because you will be able to find another surface that has a smaller capacity. So if you want to increase the minimum, when you have to there are going to be a great number of edges that are going to be involved. Actually, a constant fraction of the edges are going to be involved. So here we see there is an asymmetry. So for the lower large deviation, it will be more of surface order, whereas in the upper large deviation, it will be of volume order. So this mathematically translates by the fact that if you look at, for instance, the lim inf, this will be positive. So indeed, the upper large deviation are going to be of volume order. So now our aim is to study this deviation, but of course we have to pass by some intermediate object, and the intermediate object we want to choose must be volumic. And the natural candidate here is to study the maximal stream, because the maximal stream is indeed a volumic object, because it concerns all the edges in the set omega. So the aim of what follows is to obtain so maybe I will obtain a large deviation principle for the stream.
I assume there are lots of maximal streams, right? So there's a
Yes.
sort of
Yes.
distribution. Yeah.
Yes, but here for the large deviation principle, we are not going to obtain it actually for maximal stream, but for the existence of a stream. So we will see later. But indeed, there may be a lot of different maximal stream. So before thinking of a large deviation principle for the stream, before going stepping up into that, a most simple thing to think of is law of large number for a stream. Do we know law of large number for the stream? And the answer is again yes, we already know that. Again, thanks to Raphaël Serre and Marie-Thérèse. But before having a law of large number, you see that the object, the admissible stream object, is not really nice when we want to pass it to the limit. So before working on that, we want to actually encode this admissible stream into a measure, and then we will study the measure of this object. So now the step is, the aim is to encode this. So we are going to define a measure upon Fn. So we define mu(n) of Fn. So it's going to be a vectorial measure. So and so what we are going to do, so CE is the center of the edge E. So what we do for this measure, so here it's a Dirac in the center of the edge E. So for each edge, we are going to put a Dirac mass at the center of the edge E with the value Fn E. So here it's really a vectorial measure because I recall you that this is in Rg. So this mu(n) Fn is belongs to the set of vectorial measure of dimension d. So it takes its value in Rg and it has a value in Rg. So is this clear? So it's just a way to encode the stream Fn so that it will be more convenient to study its limit than the object Fn we have.
And the edges themselves are shrinking, right? As you're taking n larger and larger. Okay.
Yes, that's why we add this n to the power d so that we are sure that the mass on omega is bounded because of this n. So yes, a simple thing to notice is that if you look at this, so this will be smaller than something like 2dm, something like that. Just because the norm of the FNE are bounded by, you can say like 2m. So maybe here it's 4, but it will be of this order. But so thanks to that, we know that it will be a nice measure that is bounded and so on. So before involving any probability, we can just think at what will be the limit of such object, but without thinking of probability. Just the question is just thanks to the structure of this object, in the limit, what are the properties we are going to recover? Because here we have, we consider that we have an admissible stream, but we don't care about the probability in the sense that we do as if the T were all M. So that we just have a stream that is admissible, so that satisfies the node law and is equal to 0 outside omega, and we want to understand what will be the limit of such object.
A vector field? I mean, that's what it's heading for?
Exactly. Exactly. So limit. Because the thing is, in what follows, we will want to study a large deviation principle in this object. And even if large deviation principle is about studying unlikely events, there are some limits that we know we won't be able to attain because of the structure of this measure mu(n) Fn. Because of this structure, it has to converge, it has to belong to some set that has some properties, because it's not involving any probability here. It's just because of the structure of the measure. So I'm going to list these properties that we will have even when we will look at unlikely event that the limit must have. So the first thing that you said is that with this structure, it will converge towards a vector field, and it will also be absolutely continuous toward the Lebesgue measure. So this is just from the fact that we have put Dirac mass regularly spacing. It's easy to check. You can check that in the limit, the mu(n) Fn. So here Fn is fixed and determinist is fixed. So no probability. So the sequence Fn is fixed.
There's no way to engineer really bad Fn so that you get points where the vector field's not defined? So it will be
defined in the distributional sense.
So there can be points where it's bad, but for small set? Okay.
Yeah, exactly.
Okay.
So this will converge towards this, where sigma here is defined only in the distributional sense, so it's in N infinite.
Can I ask that?
So here, is the Lebesgue. Oops, sorry.
So here you're using the fact that you have this bounded M. right?
Exactly.
But this, so if you do this over the probability and not this argument that you should be able to get it also for n equals infinity, right? And also a uniform bound on the rate function, I guess. So here the rate function will go to 0 as m goes to infinity.
Sorry.
So the rate function that you have
Yeah.
above, what
Yeah.
happens to it when, so the bounds that you have when m goes to infinity?
I don't have a rate function yet. So when m go to infinity, so here we for m we will it won't go to infinity. It will remain in 0m because there are a lot of issues when you consider a low unbounded distribution, and it's harder to say that it's absolutely continuous towards Lebesgue measure. So the paper is already really technical. So at the first we wanted to not to have this restriction, but we give up having the thing in full generative. But even if you have unbounded distribution, you must have an exponential moment to have exponential decay. But here m will remain fixed, and we are going to stick to bounded distribution. I don't know if it answers the question.
Are you assuming anything on G, on the law of the increments besides boundedness? For example, if it has a big atom at 0, then by percolation considerations, there are no flows.
Yes, exactly. So yes, if there is no, yeah, you can. It works the same. Even if you have no flow, you can look at upper large deviation, as long as the atom is not restricted to 0. So we don't have any restriction on that.
Okay, thank you.
Because we are looking at large deviation.
Thank you.
There are any other questions? Okay, so yes, just by the structure of this measure, it will converge toward a vector field, and so that is absolutely continuous with respect to Lebesgue measure. And so sigma, all the thing I said to sigma, it's I won't write it formally, but of course it will be in a distributional sense. But when I will write things, I want just to simplify things, I won't care of these details, but all what I said, I will write it as sigma was a nice vector field, but it's not. But it's just to give the main idea and remove the technicalities. So this, we have this limit just by the structure of the measures, the fact that we have Dirac mass regularly spaced in the lattice. And what other properties should we have? So of course we have that this sigma is equal to 0 outside omega. So what do we have else? So how we translate the node law? So the node law means that we do not have any gain or loss of water inside omega. And for vector field, the continuous translation of this fact is saying that the divergence is equal to 0 inside omega. And we have to give boundary condition for that. And because we have to specify what happens in the boundary. So for a vector field sigma, if I say sigma x c dot n, so this may be interpreted as the amount of water at x that flows in the direction n. So what do we want in the boundary here? So here, when we are outside, when we are not in the source and the sink, we want that no water exits from there. So if we denote n omega the normal exterior unit vector. What we want is that sigma is equal to 0 on. So this is just the translation of the fact that no water exits from omega except at the sink and the source. And all of this, you can obtain this as the limit just by the fact that mu Fn is an admissible stream. So you will get all these properties just by this fact. And there is no randomness involved, it's just thanks to the structure. And last important thing that we are interested in is how does the flow translate. So if we want to know, so of course we are going to rescale, this must converge towards something that is in sigma. So if you recall that this is the amount of flow of at x that flow in the direction n. So if you want to know for sigma what is the amount of water that enters through gamma 1, you are going to integrate over gamma 1 at each point what is the amount of water that enters. So this is just the integral through gamma 1 of minus sigma c dot in omega x over. So why there is a minus? It's just because we want the flow to enter, and n omega is the normal unit exterior vector. So n omega is like that, and if you want to know the flow that enters, we have to look at sigma c dot minus n omega. So this is the definition, is the flow of the continuous stream. So what do we have? We have a discrete stream, and its flow, when we renormalize it, in the limit, it matches the flow of the continuous stream we are working with. Okay, so now that we have, so this was just for the structure, and so that we can give a name on this stream, because it will be useful in what follows, because it's we have identified the limit we will be able to reach. So it will be the sigma so just that satisfy 1, 2, and 3. And this will be useful in what? So now we go back to probability.
Yeah, yes? Sorry, just to say, is it in fact the case that any continuous flow satisfying these conditions can be realized as a limit of distributions, the way you gave before?
Yeah, that's a very good question. I hope it would. I did not find such a result, and at some point I needed this result, and I had to do other things. But actually, I don't know if such a result exists, and it's.
So it might be, for all we know, there might be other conditions that follow from this.
Yeah.
That follow through these limit
maybe,
objects.
Yeah.
Okay.
At some point, I needed this fact, and I was not able to prove it. Like, it's really complicated. If you start with a continuous flow that is not a nice flow, it's defined in distributional sense, to be able to reconstruct a discrete flow that has also all the property of not exceeding is really a difficult problem. I did not find the solution anywhere, and I did not succeed in to prove it. But it's a really nice.
So it might not be true. I mean, there may be another restriction hiding here. Okay, thank you.
Maybe, yeah.
Okay, thanks.
Thanks for the question. So let's go back to probability. So you see here, we did not miss where we remove the probability thing is on the capacity. So for so this constraint on the capacity will appear in the limit by the fact that if you look at sigma times some v, it will be smaller than nu v, where nu is the flow constant, so it's a norm. But I don't want to enter into the detail, but just remember that we have some constraint that appears in the limit on the capacity, on the restriction on how the flow can go through one direction. Oops, sorry. And so what was the question? The question was, now that we're able to define properly the limits, is to understand, do we have a law of large number for the maximal flow? So theorem. So again, as I said, so actually we can define a set sigma 0, where we add, so it's the set sigma in sigma, and we add this condition of this condition 4. That means everywhere in the domain, we cannot send more flow than the capacity allows it. So of course it's a deterministic, in the limits, it's a deterministic condition because we scale everything. And we also add that flow of sigma is equal to phi omega. Well, I recall you that phi omega was defined earlier in the previous theorem, and it was the almost sure limit of the maximal flow properly renormalized. Okay, so this set is the set of continuous streams that are limits of that may be a limit of admissible stream, and so in particular that have their flow that satisfy the maximal flow. And in fact, these flows are a solution of a max flow min cut problems, but in the continuous setting. And so what Raphael Serre and Marie-Thérèse proved is that you start with the solution of a max flow problem in the discrete setting. That is, you start with mu n fn max. And in the limit, you are able to prove that this converges towards a solution of a max flow problem in a continuous setting. So what they prove is that, depending on the domain omega, there may exist several solutions, there may exist several continuous streams that achieve this maximum. But you know that when you pick a sequence of maximal stream, you know that they will converge to one of them. So you don't know each one, but to one of them. So there exists a sigma in sigma 0 such that the limit, so it's a weak limit. Here it's a weak limit is equal to sigma. Okay, so really you start with something with a max flow problem in the discrete setting, and in the continuous setting, you end up with the limit is the solution of the max flow in the continuous setting. Okay, so now that's okay, so that's the theorem. So that means that we already know a law of large number for maximal stream. So now that we know that, we are happy with that, and we can go to, actually this is not necessary to study the upper large deviation, but it was just to let you know that this exists, and now we are going to study the upper large deviation. So principle on maximum. So I recall you that, so here it's obvious because we are studying an object that is of volume order. We expect that its decay will be also in volume order. And so with the previous work we have done, we know that the limit of mu n fn must be in the set sigma we have defined. So that means we can really restrict to this set will be really the limit, even if we look at unlikely thing, just by the structure, by the fact that this satisfies this property, it will be in the set C. So a large deviation, the aim of a large deviation principle.
And the set sigma 0, if I understood correctly, right?
So sigma 0 is for the law of large number.
So sigma 0 is the typical thing, and we're going to be in sigma. We want large deviations, we want in sigma, but not in sigma 0. Okay,
exactly, yes, exactly. So since sigma 0 is the typical thing, that means that being in sigma 0 is costless because it's just the law of large number. So when we look at upper large deviation principle, the thing we have to do here that is not clear at all is to identify a rate function. So what we want to be able to say. So here I won't work with maximal stream, but I will work with streams. So just what I want to, the probability I'm interested in is the probability that there exists Fn. So when I said there exists Fn is in the sense of it's an admissible stream, Fn an admissible stream, such that mu n Fn is close to sigma and so this I won't I will always remain a bit floating on that. I will not specify what this, but there is a distance here involved. Okay, and so the aim of to derive upper large deviation is to be able to identify the rate function and to say this is of order nd to some rate function sigma. So this is our aim. Because this is the first step to obtain a large deviation principle is to identify the right rate function.
But will that be strong enough to deduce about the value of the stream? I mean, is this topology, is this equivalence that you wrote here strong enough to allow you to deduce things for the maximum? For the flow?
Yes. So I will explain that later, but of course we are doing that in order to be able to derive our main objective was to be able to obtain a large deviation principle for maximal flow. And we will, I will briefly sketch how we can from this, from the large deviation principle, be able to derive a large deviation principle for the maximal flow. And so, yes, so we have to identify this. But here, actually, it's not really nice because it's not really explicit. So we want something a bit more explicit, but still not totally explicit. So we want to express this using an elementary rate function. So what do I mean by that? I mean that this is already a complicated event because the sigma may be really complicated. And we want to think for stream what can be a really elementary event. And the most elementary stream we can think of is a constant stream. And the most simple domain we can think of is a cube here, because a cube is easy to, when we want to merge two cubes. So before defining this rate function, we want to define an elementary rate function. And so we are interested in this probability. So here in a unit cube, still admissible stream, we do not put any, here we do not put any constraint on the boundary. Everything is source and sink. There is no source and sink, but just it has to satisfy the node law inside and the capacity constraint, such that mu n Fn is indicator. So this is the most elementary thing we can think of that will be easy for later. And this, we can prove that this thing, when we rescale it by 1 over 1 to the power nd and we put a log, this will converge. So we will be able to identify. So this will enable us to identify this. So it's not totally explicit because this is not totally explicit, but it will enable to here have something more explicit in terms of this thing, but that is of course not totally explicit. So this is the elementary cost. And of course, for when you have more complicated function, if you want to have the total cost of the thing, you are going to integrate the local cost. So the function E sigma will be just the integration of all the local costs. So we are going to integrate over the domain all the local irregularities. So we say that the total irregularity is just the sum of the local irregularities, where the irregularities is given by this. So it's just, okay, so this is more explicit. So we are able to obtain a rate function that is given as the integral of the more elementary rate function. Okay, and so now I want to state a proper large deviation principle. Okay, but you see, to do so, the large deviation principle, so mu n fn, has its value in this set. So where here's the measure on RG. So I have to give, so I have to give values for the rate function. For the moment, I only gave value for the function that were in sigma, but I have to give values to all the functions. But as I said, with the study we did earlier, since the limit must be in sigma without any probabilistic consideration, that means that the overall limit are unreachable. And when you are unreachable, it translates for the rate function by the fact that the rate function is equal to infinity for the over points. So now that we can define an over rate function, so it's a lot of I, so sorry for that. So the real rate function, so that is going to be defined on the set of measures this time. So for this real rate function, so we say that it's plus infinity if nu is not in sigma LD. So sigma is not sigma LD. So I write this, but if if nu is not written as sigma LD, such that sigma is in sigma. That's what I mean by that. So this is what I said just because of the structure. And otherwise, we say that is E hat sigma if sigma in sigma. So yes, maybe in sigma, I should also add some condition about the M, because I said it was in infinity, but I have to add another condition on the norm, but it's okay. Okay, so we have a lot of rate functions. So we have I without a hat that is the elementary rate function, I with a hat that is the rate function when we have a sigma, and Itila that is the real rate function that we are going to use to prove a large deviation principle. So now I can state my theorem. So, so the topology is it's not the weak topology, but it's topology associated with the distance that we have that we can relate to the weak topology, but I don't want to enter into the details. So there is a topology such that the lim inf of the lim, so it's the lim inf lim sup of the exactly same thing. So this is smaller than okay, and so the topology, I don't enter into the detail, but it's related to the distance that we use, but we can relate that to weak topology. Okay, so we have this, so this is really a large deviation principle. And as you can see, it's not on the maximal stream, but on a stream. It's a probability. So in some kind of sense, it's a probability on the environment. The probability that there is an environment such that we can create a stream that looks like. So this is answering. And now the natural question is how this can be useful in what follows, so to deduce a large deviation principle for the maximal flow. So what we want to study is the probability that phi n is greater than lambda minus 1 for lambda strictly greater than phi omega, where we told you that phi omega was the law of large number where it converges. Okay, so that's what we want to study, and actually this is exactly equal, because if the maximal flow is greater than lambda n to the power d minus 1, it means that there exists a stream Fn such that its flow is greater than lambda n to the power d minus 1. So this is just by definition. And then with the distance that we have, we will actually have the continuity of the flow, meaning that if mu n Fn is close to some sigma Ld, then the flow will be close. Small. So actually, this thing we can say that it's approximately the probability that there exists. Maybe I will. The probability that there exists a stream Fn such that mu n Fn belong to the set of sigma in sigma such that okay, and this is over there. Here we can just apply the large deviation principle, and we have an override function j lambda, because here you see if you apply the what you will here you replace this thing with the set A that is this. So this will just get you that you will be interested in this infimum. So the infimum of E sigma for sigma in sigma such that so there is a lot of approximation here, but that's really where the idea is. You know that the fact that there is a flow, there is a stream with a flow greater than lambda to the power n d minus 1 means that this stream is going to be close to some stream that itself has a flow greater than lambda. And thanks to the fact that we have large deviation principle for streams, we can deduce a large deviation principle for maximal flow. And so if you are aware of large deviation, this is, you may have recognized that is a kind of contraction principle, because this function flow is continuous. So you cannot directly apply it, but you can prove it exactly in the spirit of contraction principle. And so actually to prove then a full large deviation principle for phi n, we also need to know the lower large deviation principle that we are still writing right now with Marie-Thérèse. But the thing I wanted to insist on is that the fact we have a large deviation principle on stream enables you to deduce the main ingredient to get a large deviation principle on the maximal flow. So, okay, I plan to speak about the proof, but maybe it's too late, but maybe I can just say very quickly a word about that. So for the proof, the aim is first, as we already said, the first step is to be able to prove that, that this limit converge, that we will be able to have a conversion, so that there exists an elementary rate function. And here, when you want to prove this, you will do in 2 steps. You will prove the lower bound and the upper bound. So there is a step that is simpler than the other. So I don't know how much time I have, because maybe I won't.
I think it's better to leave some time for questions.
Yes. Okay, so maybe yes, I just. So I will just take 1 or 2 minutes. So yes, so to prove this, I will just say it orally, and if you don't understand, I'm sorry. So to prove this direction, it's the easiest one, because you have to deconstruct. So you have a stream, and you just say, I have a stream in the whole omega. Then I can decompose this omega into cubes, and I will be able to recover easily elementary events. And I can relate these elementary events to the full rate function. But in the other direction, you start with elementary events. That means you start with streams in cube, and you want to reconstruct that to construct a stream that in the whole omega that is close to sigma. And this step is really, really technical. So there are a lot of things to do. In particular, you want to reconnect streams in cubes. That means you have streams, you have here, they have some input, and here you have some output here, some input here, and you want to be able to properly reconnect it, but without taking too much room here. And this is really complicated, technical. And also you want that the whole stream that you build, you want it to be to remain contained in omega. And all of these things are really technical, but you can do that. And once you have reconstructed this stream, you can prove the other direction. And this is really the once you have this, the remaining follow easily. So maybe I will stop here. Thank you.
Let's thank the speaker. Any questions?
Oh, I have another question. Is it possible to say something about your rate function J? So in particular, I mean the rate function for the actual maximal flow. In particular, I guess there are cases where it's not necessarily continuous.
So yeah, it's convex.
No, this I find surprising because of the reason I mentioned earlier, namely, if you allow an atom at 0 and you don't have a flow, so then you need to raise it to a percolation level, and that costs a constant cost.
Yeah.
So it cannot be continuous. But the question is, except for this problem, or if you make more assumptions on G, do you get something nicer?
I think except the extremities, it's continuous. Yeah, but we can really, maybe sorry. Yeah, I have to check it.
Because I'll tell you, because in particular, the issue I'm seeing is here you're looking at greater or equal to lambda. But this doesn't show that you can achieve exactly lambda, say. So this is kind of a lower envelope of the true rate function. The true rate function could, in principle, jump up and down. I don't see. So do you have a monotonicity? For example, do you have a monotonicity argument for the true rate function?
Yes, we have monotonicity. No, but actually I remember that we were also quite surprised, but even if you have an atom in 0, it remains continuous.
How? You need to
but it's really like
you need to get a percolation going. I don't understand. But if you have a big atom at 0, imagine that the probability at 0 is 0.9, then you don't have any legal flow, period.
Yeah,
because,
but yes, but you want, what you want is to let path of flow that circulates through the thing.
right.
So it will cut it if you just look at some you want it to be just greater than some epsilon. Okay, because here the phi omega in what you say, it's 0. Okay.
Yes.
In this context, so if you want just to increase a little bit, it will involve
But you have to have percolation, no? You have to have the non-zero edges have to percolate.
yes,
I think
but
she's saying that the cost of changing the
is volumic.
The cost of creating a cut
Yeah.
in the subcritical percolation is you can control this probability.
Yes, it's volumic. Like, because
Yes.
if you need to increase, maybe I can write. If you want to, so you have phi omega is equal to 0, and
Yes.
if you want phi omega greater than epsilon, some epsilon.
Yes.
But so what you will need to create is like an order of a small an order of n(d-1) paths that are of length n.
I see.
And for this, you will change the
I see. Okay. Thank you. So it's continuous and it's monotone. The rate
Yes.
function J.
Yes.
Okay. Thank you. Thank you.
Any last questions?
I had a question. So this was a very nice talk. Thank you. You spoke about the law of large numbers and the large deviation principle. What is conjectured or known about the moderate deviations, about variance, for instance, of the flow?
Yeah, I think it's usually this interpretation of first passage percolation is kind of lagging compared to the other interpretation of first passage percolations.
It is equivalent to first passage percolation, so everything that is known there should be true here as well?
Yeah, actually you can see this interpretation as the high dimension version of the standard one, because in the standard one, what you do is you minimize the sum over path when you look at geodesic. And here, because it's related to minimal cut set, you minimize sum over cut set. So usually usually the result that has been obtained in first passage percolation, classical interpretation may be extended to this interpretation.
Sorry, I just didn't fully understand. If you work in 3 dimensions, then the first passage percolation problem is equivalent to the flow problem that you described, or these are two distinct?
In 2 dimensions.
No, but in 3 dimensions.
Yeah. So sorry. So in 3 dimensions, can you repeat? Sorry.
In three dimensions, is it that the two problems are the same, or are they distinct problems in 3 dimensions?
Yeah, distinct problem.
Okay, so it is not obvious that the variance is unknown for this problem, but you say that in fact nothing more is known.
Yeah.
And there are no conjectures whether the variance, say, is big O of 1 in a high enough dimension or not?
No, not I'm aware of.
Right. Yeah, I mean, in the proper scale. Thank you very much.
Okay, so let's thank the speaker again. You can unshare yourself.
Yeah.